Good day, I'm Norman Wildberger. In today's video we're going to look at singletons and vexils and the rank of a maxil. We're going to define what the rank is and aim towards this rank theorem. So where we are so far, we've defined things called singletons, which are just lists of natural numbers. We have pixels, which are lists of pairs of natural numbers. A vexil is then a multi-set of singletons, and a maxil is a multi-set of pixels. And then we have these types: sing for singleton, pix for pixel, vex for vexil, and max for maxils. So in this video today we're going to associate vexils to the rows and columns of a maxil, so allowing us to move more freely from two-dimensional objects to one-dimensional objects and back and forth. And to make that a little bit easier, we'll define multiplication of singletons with pixels. Then we're going to move towards the rank of a maxil and this rank theorem. So we want to talk about rows and columns of a maxil, but we need to be perhaps a little bit more precise about what those words actually mean. So recall that if we have a maxil M and we multiply it on the left by this idempotent element EII, and that's the maxil that just has a single one in the ith position, then what we get is we get the restriction of M to the ith row. Everything else is replaced with 0, and just the ith row remains. While on the other hand, if we multiply a maxil by an idempotent like this EJJ on the right, then we restrict the maxil to the jth column. The jth column stays where it is, but everything else is replaced with 0. So for example, here's a maxil M. We multiply it by, in this case, E33 on the left. And you can check by doing the multiplication that what you get is the maxil, which is just the third row of the original maxil, and everything else is zeros. On the other hand, if we take that same maxil and multiply it on the right, say by E22, there's E22, then what we get is just the second column of the original maxil, and everything else is replaced with zeros. So this is certainly one interpretation of what we mean by the row and column of a maxil, that the third row of this maxil is that maxil, and that the second column of this maxil is that maxil. But we want to have also another possible way of thinking about what the rows and columns of a maxil are. What we are going to want to do is to define the rows, say the ith row of a maxil or the jth column of a maxil, as a vexil. In other words, as a one-dimensional object, not as another two-dimensional object. So for example, if this is the maxil M, we are going to want to define the third row of this maxil as being that row there, but actually as a one-dimensional object, in other words, as a vexil. So that R sub 3 of M is the vexil 7, 4, 25, 23. No longer a maxil. You can see it doesn't look like a maxil because it's supported on a frieze rather than on our screen. And here is the second column of M, 3, 2, 4, 5, but written out as a vexil, also a column vexil, with a frieze notation. Okay, so why would we want to do this? Well, it's because we want to look at the interaction between, say, rows of a given maxil. We might want to, say, add this row to that row. But we don't want to do this at the level of pixels, because then we have to keep them separate. This 4 represents a certain number of pixels of the kind 2, 3. This 2 represents a certain number of pixels of the kind 2, 2. We can't add those without things just staying separate. But when we replace these things with one-dimensional vexils, then we are in a position of doing the usual arithmetic with vexils. That's what we want to do. So to do this efficiently, we are going to define the product of a singleton and a pixel. So we're going to extend our multiplication of pixels, which was really at the heart of this entire arithmetic, to an arithmetic also involving singletons together with pixels, in either order. Okay, so how does this product of singletons and pixels work? Well, it's very much like the product of pixels. So here is a singleton K, and here's a pixel LM. We're going to define the product of these two things to be the singleton M if K equals L. So if we have agreement between these two natural numbers and the product of these two things, this singleton with this pixel, is this singleton. And if this condition is not satisfied, we're going to have emptiness. This rather novel, new kind of multiplication possibility. Now what we get is not something with a name or a symbol associated with it, it's just blank on our page. And similarly, when we multiply them in the opposite order, so if we have Lm on the left and K on the right, then again we're going to get a singleton, but it's going to be L this time if M equals K. So if these two agree, we'll get L and blank otherwise. So for example, the singleton 3 times the pixel 2, 4 is blank, because these two are not the same. The singleton 2 times the pixel 2, 4 is the singleton 4, because this 2 and this 2 agree. The singleton 4 times 2, 4 is blank, because we have to have these two agreeing. The fact that these two agreeing doesn't do anything for us. On the other hand, if we have a singleton on the right, say 3, 5 times 3, well, that's going to be blank because we require this and this to be the same. And 3, 5 times 5, well, these are the same, and we're going to get the singleton 3. Okay, so this multiplication of singletons with pixels now extends to a multiplication of vexels with maxils. Because a vexel is just a multiset of singletons, and a maxil is just a multiset of pixels. So if we know how to multiply singletons with pixels, then we can multiply m sets of singletons with m sets of pixels. And we do that in the standard way that we're now getting used to, that we just multiply all possible products of the m set objects in the first m set times the m set objects in the second m set. We look at all possible products and put them all in a big box. Okay, so we want to define this notion of a row or a column of a maxil, but at the fundamental level of multisets, where the thing actually is defined. So we don't really want to rely on our picture of our maxil with our screen and those numbers and say, well, we're just going to circle this row. That's a visual or geometrical interpretation, right? It relies on our pictorial understanding of what we mean by a row. So we want to have something that's a little bit more precise. And here is going to be our official definition of what the ith row of a maxil is, or what the jth column of a maxil is. And as I said in the previous slide, we want the ith row of a maxil to actually be a vexel, similarly for the jth column. So the definition is going to rely on this particular kind of special kind of vexel. Okay, it's a vexel that contains just a single singleton, namely the singleton list I. Okay, so this here is a vexel with one element. And we're going to define our I of m, the ith row of the maxil m, to be ei times m. So m is a maxil, and ei is a vexel. How do we multiply a vexel times a maxil? Well, I've just told you we multiply all the singletons in this vexel with all the pixels in this maxil. Take all possible products. And similarly, the jth column of m is going to be the vexel cj of m, which is m times ej, with the ej on the right-hand side. Okay, so let me illustrate this with this example. So here is a maxil m, 1, 0, 2, 3, 1, 0. And this is really the following multiset. Okay, it contains the pixel 1, 1, 2 copies of the pixel 1, 3, 3 copies of the pixel 2, 1, and 1 copy of the pixel 2, 2. So the second row, let's look at the second row, which we sort of visually see as 3, 1, 0. How do we get at that? Well, we take E2 times M. E2 is this vexel right here. It's the vexel containing the single singleton 2. Okay, so there's a vexel, and here is this maxil M, just rewritten again. So to multiply this M set with this M set, we have to multiply all the possible products between the entries of this M set with the entries of this M set. Now there's only one entry of this M set, namely the single singleton 2. So we have to multiply this singleton 2 with this pixel 1, 1, and the singleton 2 with this pixel 1, 3, and so on all the way up to this singleton 2 times this pixel 2, 2. We have to put all the results of those multiplications in a box. Okay, so what do we get? When we multiply this singleton 2 with this pixel 1, 1, we get emptiness because this 2 and this 1 do not agree. Similarly, this product is empty, this product is empty. But this product is not empty because that 2 and that 2 agree. So the result is the singleton 1. Similarly here, we get the singleton 1, here we get the singleton 1, and here we get the singleton 2. So R2 times M is this vexel. It's a bunch of singletons, so it's a vexel. And what vexel is it? Well, there's 3 1s, and there's 1, 2. So in our Fries notation, if we write it as a row vexel, it's 3, 1, 0, which is 3, 1, 0. So basically we're looking at all the pixels involved in the Maxwell M, and we're disregarding all of the ones that don't start with 2. Okay, that's what we're doing when we're multiplying with this 2. We're disregarding all the pixels that don't start with 2. The ones that do start with 2, well, we're just essentially copying their second entry. That's what the multiplication does. So really, we're just picking out that second row and copying it, but copying it as a vexel. Copying it as a bunch of singletons rather than as a bunch of pixels. Okay, what about, say, the third column of this thing? To get that, we multiply the Maxwell M with the vexel consisting of the singleton 3, E sub 3. So here we have to do all possible products between this singleton and these various pixels. But this one times this one is empty. This one times this one, we get something because this second 3 agrees with that 3. We get 1. Here also, this second 3 agrees with that 3, so we get 1. Here there's no correspondence, emptiness, 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 emptiness. We just got a pair of 1s, which is, when we write it down as a vexel in column form, is the vexel 2. Or 2, 0, it's the same thing. So again, what we're doing when we're multiplying by this E3 is we're looking at all the pixels in this Maxwell and disregarding all of the ones which don't have a 3 as their second entry. All the things that are not having 3 as a second entry are basically being ignored or killed. The ones that do have 3 as their second entry, the result of the multiplication is just to give us the singleton consisting of their first entry. So basically what we're doing is we're copying that column but replacing the pixels with the singletons of just their first entries. That ensures that we get a vexel where we started with the Maxwell. Okay, so we see that we have to have a kind of a appreciation for this data structure point of view. Right? We have to keep straight that we've got lists and we've got M sets, and here we have a M set containing a list. We have to keep this in mind. The way we multiply M sets is very critical. So those of you who have taken a classical linear algebra course will probably see this approach as being overly fussy. We're spending a lot of time on the actual fundamental nature of the underlying objects. And that's, of course, in keeping with this being a Foundations of Mathematics series. But you should also appreciate that there's some sloppiness in the usual approach, where we define things purely pictorially. Say, matrix is something that looks like this, and a row is something that looks like this, and we're using our visual geometrical intuition and allowing definitions which are just at the pictorial level. Right? There's something imprecise about that. And it's clearer if you try to compute in this framework. Right? If you get your computer to try to program something in this language, then you have to think about how you're going to translate all those pictorial statements to actual precise statements that a computer can understand. So one way of thinking about what we're doing here is that it's providing some kind of framework for a computer or a computer scientist or a programmer to create a kind of viable computer linear algebra. It's a way of thinking about it. Okay, so once we have the rows of a maxil clearly defined as vexels, we can discuss linear relations between them. Because once we're at the level of vexels, we can add vexels. We can add vexels because they're both m sets, and we can always add m sets. And we can multiply m sets by scalars, and so we can take linear combinations of vexels. So that means we can take linear combinations of rows of maxils, which we couldn't so easily do before in the purely maxil world. So for example, here's a maxil M. Okay, and so let's refer to its rows as R1, R2, R3. So R1 refers to this row, but as a vexel. There's R2 as a vexel, there's R3 as a vexel, there's R4 as a vexel. Okay, so at the level of vexels, we can see that in this case, R3 equals R1 plus R2. There's a relationship between this vexel and this vexel and this vexel. Namely, if you add this one and this one, then you get this one. And this fourth one is 4 times this one minus 3 times this one. So it's 4R1 minus 3R2. Now, in order for this to work smoothly, as you can see, we want to extend our coefficients to allow integers, to allow negative numbers, so that we can take more general linear combinations, not just always positive linear combinations with natural number coefficients. And in fact, we probably also want to extend things to have rational coefficients. Then we can do standard rational mathematics at the level of these coefficients. And this gives us the flexibility of usual linear algebra approach, where we are allowed to take rather general linear combinations of things. Now, it's not entirely necessary to do this, so we could rephrase these linear relations if we really had to by removing the negative signs and removing all fractions. We could multiply through by common denominators, and we could bring the negatives over here, for example, to this side here, and restate these relations purely in terms of positive natural number linear combinations. But it's more natural, I think, especially for someone who's taken a linear algebra course, to think about it this way. So what we're going to be doing is thinking about a maxil as being an array like this, or an M set of pixels, just as before. The definition of pixel hasn't changed. The pixel is still a list of natural numbers, but the multiplicities of those pixels is allowed to be integer valued or possibly even rational valued. Okay, so in this case here we see that we can now talk meaningfully about relations between rows, or we could also talk about relationships between columns, same thing, where we regard the rows now as actual vexels, where the linear combinations of vexels really is allowed because those are just M sets of singletons. Okay, so we want to now introduce the idea of the rank of a maxil. And we'll do that by having a preliminary discussion about row rank and column rank. And shortly we'll see that those two notions actually agree. But it's not obvious at first that they agree. So the row rank of a maxil M is defined to be the minimum number of vexels needed to express each row of M as a linear combination of the vexels. So we're looking for a collection or a set of vexels which is as small as possible but still has the property that every row of our maxil is some linear combination of the vexels that we have in our little list. And a similar definition of column rank: minimum number of vexels needed to express each column of M as a linear combination. So here is an example. Here is maxil M, and I claim that the row rank of M is actually 2. So that means we have to find a set of vexels with 2 vexels so that everything here is a linear combination of those two. And I claim that these two vexels will work. In fact, I can just take the first row and the second row. I don't have to take actually rows of the maxil itself. I'm free to take any vexels that I like. But I do require that every row of the maxil is some linear combination of the vexels that I've chosen. So why does this work? Well, because this first row is obviously a linear combination, it's that one. The second row is obviously a linear combination, it's just that one. And this third row, 665, is 2 times the first row plus the second row. Well, you can see that. 2 times 1 plus 4 is 6, 2 times 3 is 6, and 2 times 2 plus 1 is 5. So this is a legitimate linear combination expressing the third row as a linear combination of these two. So these two alone suffice to span the rows of the maxil. We use that word. That is that every row here is a linear combination of these vexels. And this is the minimum number required. We can't do it with just one vexel. If we dropped one of these, then that wouldn't be enough. So the minimum is 2. That means that the row rank of this maxil is 2. Okay, so here we come now to a pretty hefty theorem. This is really a major theorem in linear algebra. But it's now stated in this language of maxils. But both the statement and the proof are pretty standard in linear algebra. Okay, the statement is that for any maxil m, the row rank of m equals the column rank of m. The minimum number of vexels needed to span the rows equals the minimum number of vexels required to span the columns. So here is a sketch of the argument, and I'm going to sort of use an example to illustrate what's going on. I think it makes it clearer. So suppose that V1, V2 up to Vk are a minimal number of vexels which span the rows of a maxil m. So we're given a maxil m, and we found one way or another k vexels v1 through vk which span the rows of this maxil m. We can use these to obtain a factoring of m of a particular kind. So it turns out that we can then write m as a product of 2 maxils, where the second maxil is obtained by taking these k vexels that we have and putting them as the first k rows of a maxil. And the other component in this product on the left-hand side is a similar kind of thing where we have k vexels written as columns, say u1, u2 up to uk, where it turns out that u1, u2, and uk span the columns of m. So given a minimal number of vexels which span the rows of a maxil m, we can cook up this factorization of m, and it's called a full rank factorization. And it's really the existence of this factorization that allows us to say something about having vexels which span the rows gives us columns which span the columns. So that's what happens. If these things here span the rows, then these ones here, these columns, will span the columns of m. Okay, so I want to illustrate this and why it's true with an example. This argument really does rely on our understanding of the geometry of maxil multiplication. So let's have a look at this very illustrative example here. So here's a maxil m. Okay, and if we look at its rows, let's say we're interested in the rows, and we're asking, well, what's sort of the minimal number of vexels required to span those rows? Well, one thing would be to just start looking at the rows themselves and asking how many of them do we need in order to span all of the rows. Well, a little bit of thought shows that these first 2 rows will suffice. So if we just look at these first 2 rows, this third row is a linear combination of these 2 rows. Namely, it's this row plus this row. And this row here is 4 times this one minus 3 times this one. Right? We've seen this relation before. So we've already observed that these two are spanning rows of this maxil. Now, we can use that fact to get this factorization. So this is the sort of key point, is how we go from the fact that these are spanning rows to this factorization. So let's just look at this product where on the right hand side we just put the maxil with just these rows here. 0, 1, 2, 0, 0, 1. I'll dispense with the zeros outside. Okay. Now, I claim that we have this product. Okay, so let me remind you of the way the maxil multiplication works. If we're interested in this first row here, okay, the first row of the product is obtained by taking this times this. So how do we get this thing? We get this times this plus this times this. And then how do we get the entry here? We get this times this plus this times this. How do we get the entry here? We get this times this plus this times this. So what we're doing is we're taking a linear combination of rows where the coefficients are given by these numbers here. So this is a kind of important observation. To get the first row of a product, what we're doing is we're taking linear combinations of the right-hand rows with the coefficients determined by the first row of the left-hand side. Okay? So this thing here is telling us that 1 times the first row plus 0 times the second row gives us the first row here. This second thing here is telling us that 0 times the first row plus 1 times the second row is this row here. That's true. The third one is telling us that 1 times this first row plus 1 times the second row is this row here, the third row here, which is correct. And this one here is telling us that 4 times the first row minus 3 times the second row gives us this row here. Right? So these numbers that are appearing here are the coefficients required to express these various rows here as linear combinations of these rows here. Please make sure that you go through the multiplication and convince yourself of that. So in this case here, the spanning set are these vexils 0, 1, 2 and 0, 0, 1. Those are the vexils that we need to express all of these as linear combinations, and we've been able to create this factorization from knowing that. Let's have a look at the same maxil M, but choose a different set of vexils which span the rows. Right? The set of vexils which spans the rows is highly non-unique. There's a lot of choice. In particular, we could choose 0, 1, 0 and 0, 0, 1. Now these are not rows of the original maxil. That doesn't matter. All that we require is that each of the rows here is a linear combination of these rows, and that no fewer rows suffice. So let's check that. So the way the multiplication works, this row here is 1 times this row plus 2 times that row. We express that with the 1 and the 2 here. So 1 times this plus 2 times that. 1 plus this times 2 times that. 1 plus this times 2 times that. We're taking 1 times this row plus 2 times this row to give us that 1. At the second row level, this 0, 0, 1 is 0 times this row plus 1 times this row. At the third row, we're getting 0, 1, 3. This is 1 times this one plus 3 times this one. It's particularly simple here because of the nature of these. And 0, 4, 5 is 4 times this one plus 5 times this one. So again, what we're seeing is that we've got our set of spanning vexils forming the right-hand matrix in this factorization, and the left-hand matrix is just recording the coefficients required to express the various rows as linear combinations of these. In particular, note that the number of columns here is always exactly equal to the number of rows here. If there are k rows here, then there are going to be k columns here, because we need to say how many of the first row we're going to need, how many of the second row we're going to need, how many of the third row we're going to need, all the way down to how many of the kth row that we're going to need for each one of these rows. So the factorization always has the property that the number of rows here equals the number of columns here. Okay, so the argument is that once we have a minimal number of vexels that span the rows, we can cook up such a factorization. And then the observation is that we can interchange the rows and the columns in our thinking. Right? Things are symmetrical with respect to rows and columns. So when we look at a product like this, we can say, ah, this is a linear combination of these rows with these as the coefficients. That's true. But an equally valid interpretation is to say, aha, this is a linear combination of these columns with these as the coefficients. So let's illustrate that. So this first column here is obtained as a linear combination of this column and this column. It's 0 times this first column plus 0 times the second column. The second column here is, here's a second column here, it's 1 times this column plus 0 times this column. And this third column is 0 times this column plus 1 times this column. It's even clearer up here. If we look up at this thing here and we look at this third column here, this third column, what this is telling us here is that this third column is 2 times this first column plus 1 times this second column. So if you take 2 times this first column and add 1 times this column, you're going to get this column here. So there's a symmetry. This kind of factorization can be interpreted as we're taking a linear combination of these rows with coefficients determined by what's happening on these rows here. Another way of thinking about it is this is a linear combination of the columns of the left-hand matrix with coefficients determined by what's happening in the columns of the right-hand matrix. Okay? And it's this symmetry which is the key to things. So what is this saying is that once we have a factorization like this, then we know that we can express the columns here as linear combinations of these columns. And we know that there are at most k columns here by the construction. So that's telling us that the column rank of m is always less than or equal to the row rank of m. If we've found k vectors or vexels which span the rows, then we found at most k vexels which span the columns, namely the columns of the left-hand matrix in this kind of factorization. Okay, now by symmetry, everything is completely symmetrical. If we've just proven that the column rank of m is always less than or equal to the row rank of m, we just interchange the argument. Then the row rank of m is always less than or equal to the column rank of m, and so these two numbers must actually agree. And we get this common number, which is the rank of m. Okay, so it's a great exercise to see how this works in practice. So as an exercise for you, write down some maxils and find factorizations like this. So find actual minimal row vexels that span the rows. Write down a corresponding factorization and convince yourself that you're also getting at the same time a minimal set of column vectors, or column vexels, which span the columns. We're going to be returning to this as an important little factorization, and the notion of rank is all important in linear algebra. It colors many aspects of the subject. So we are going to be going a lot further in this direction of maxils and so on, and sort of building up linear algebra, but I want to give you a little bit of a break from that and talk just for a few lectures about something else which we are going to have to address in this discussion at some point. Okay. So we've been talking a lot about the importance of finite, concrete, write-downable expressions. You all know that I'm very much against sort of waffly statements about all the natural numbers or infinite sets here or infinite sequences here. And although I've talked earlier in this foundational series about the difficulty with very, very big numbers and sort of making phrases about infinite sets, I want to talk a little bit more about that, really hammer home the importance of thinking clearly about how we represent numbers and what actually is possible and what is not possible. So we're going to have a little bit of a disruptive look at large numbers in our next video, with a view of explaining why we want to stick very clearly in this finite, concrete, write-downable framework that we're proposing. Okay, that's going to be kind of a central theme of ours, and I think it's going to be a central principle in 21st century mathematics too. Right? We're going to have to give up on the fairy tale of infinite this and infinite that. And one of the best ways of really seeing why we need to do this is to see the difficulties that are there in the natural number realm once we get to biggish numbers. Okay, so we're going to look at some reasonably seriously big numbers next time, and you're going to start to see some of the problematic aspects of arithmetic with big numbers. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.